Welcome to this lecture. This is the second lecture of week 5. In the previous lecture, we have discussed about sufficient conditions under which we are having almost sure convergence of series of independent random variables. Now, there we had looked at certain conditions involving expectations and variances which led to the two series theorem. We had also looked at the truncated version of the random variables which led to the three series theorem, which gave us the necessary and sufficient conditions for the almost sure convergence of such series of independent random variables. In this lecture, we are going to look at a somewhat similar problem. Without further delay, let us continue discussing using the lecture notes. So, these are some of the standard notations that we are already using. So, we are having some specific probability space, and on top of that we are given a sequence of random variables xn, and corresponding to the sequence we have the sequence of partial sums, and of course a related quantity of interest is the sample mean, which is Sn over n. So, these things we have already used earlier in our discussions, and now in the present lecture what we are going to look at are limiting behaviors of this sample mean. Now, in the following discussion, typically we are going to assume that all these random variables in our discussion are in L1, meaning they are integrable, and in particular their first absolute moment are finite, and in particular the expected value therefore will be a real number. And as an application of that, we are going to get that expected value of the sequence of partial sums, that also will have finite expectations, and similarly for the expectation of the sample means. Now, with that setup, we discuss the question of interest in this lecture. We are going to discuss something called the law of large numbers, and this has two variants. The first variant is typically called as the weak law of large numbers. We are going to say that the sequence of random variables in our question satisfies the weak law of large numbers. So, in short we are going to write WLLN if Sn minus expected Sn, so that is centered, divided by n converges to 0 in probability. So, in probability convergence to 0 for these centered random variables is going to be called the weak law of large numbers if the convergence in probability holds. And similarly, there is a related convergence notion that we are going to consider, and that is what we are going to call as the strong law of large numbers. So, we are going to say that the sequence of random variables in our question satisfies the strong law of large numbers. Again, in short we are going to write SLLN if Sn minus expected Sn, so again the centered random variables divided by n converges to 0, but in a stronger notion of convergence, which is almost sure convergence. Recall that almost sure convergence implies convergence in probability. So, therefore, in case the sequence of random variables xn satisfy the strong law of large numbers, it will also satisfy the weak law of large numbers. Now, what we are interested in are sufficient conditions on the sequence of random variables which will ensure whether the weak law of large numbers or the strong law of large numbers holds or not. So, let us continue. So, in this setting there is a more general form that will also be of interest. So, instead of the specific form that we have used, which is Sn minus expected Sn divided by n, instead of that sequence we sometimes are interested in a different scaling of this same sequence. What we are going to ask are, there should be certain real sequences which we denote by an and bn, such that Sn minus an divided by bn, that quantity either in probability or in the almost sure mode converges to 0. Now, you see the earlier framework where we had Sn minus expected Sn divided by n, that is of course a special case of this where an is equal to expected value of Sn and Bn is equal to n. So, if you make these specific choices, you go back to the earlier case that we have considered. So, most of the time we are going to use these expected Sn and divided by n as our special choices for an and bn. And if the convergence in probability holds, we are going to say that weak law of large number holds. If the almost sure convergence holds, we are going to say the strong law of large numbers holds. Alright. So, now important comment that we are going to use in our later discussion is this, that if x is in L2, that means that the second moment of x is finite, then as a consequence we also have the variance being finite. So, remember, variance is the minimum of all second moments about a point, and in fact if the second absolute moment about 0, that is given to be finite. So, therefore, variance is also finite. We are going to use this immediately in our next result. So, the idea is this, we are going to consider a sequence of random variables now in L2. So, therefore, we can talk about their first moments as well as second moments and variances. So, we assume further that all these random variables are mutually independent, and next that the variance of all these random variables are uniformly bounded by some m. So, this m does not depend on the choice of n. So, it should hold for all n greater or equals to 1. So, here it is important that we are looking at this sequence of random variables coming from L2. All we are asking is that they should be mutually independent and the variance should be uniformly bounded. We are not asking anything about the relations involving the distributions of xn's. They could be different, but as long as the variance has a common bound, we are going to look at the corresponding result. So, under these assumptions, the conclusion says that the weak law of large numbers holds for this specific sequence. Let us look at the proof of this result. So, we start by looking at the independence of xn's and the application of that to the variance of Sn. You see, Sn is the sum of x1 up to xn, and since these are all independent and already in L2, we just split it as a summation of all the variances. So, this observation was mentioned earlier in note 6 of week 4, please go back and check. But now we have assumed that all these variances are bounded above by some number capital M, and there are n many such terms. So, the total summation is dominated from above by small n times capital M. Now, once we have that, look at the second moment of this quantity. So, Sn minus expected Sn divided by n, that random variable we are looking at the corresponding second moment. If we simplify this, we are going to get, first of all, 1 by n square comes out of the calculation, and the remaining portion is nothing but variance of Sn, for which we have the upper bound. So, therefore, the term in question, the second moment that we are looking at, can be dominated from above by m over n, and this is true for all n, and therefore, as small n goes to infinity, we have that this second moment goes to 0, which means that Sn minus expected Sn divided by n actually converges to 0 in the L2 space as n goes to infinity. And of course, L2 convergence implies convergence in probability. This was discussed earlier in proposition 3 of week 3, and therefore, we have the required in probability convergence of Sn minus expected Sn divided by n to 0 in probability. But now, here we have assumed that the random variables are in L2, they are mutually independent and the variance are uniformly bounded. Now, this same result can be established under further weaker assumptions. So, let us see. So, if these random variables are still in L2, but these xn's being uncorrelated, then what does it imply is that for each n and m, the covariance between xn and xm is 0. This was discussed earlier in note 6 of week 4. Please go back and check. But now, if these covariances for distinct n and m are 0, then what happens is that variance of Sn can be simplified in this way, that it is first of all the variance of this sum of random variables and now you expand. So, first you have the variances of individual random variables and then the cross terms which are exactly given by the covariances. But since all of these are 0 for distinct I and j, you end up having just the summation of variances. So, therefore, our earlier result about the weak law of large numbers can be restated for this situation when we replace mutual independence simply by uncorrelatedness. So, we are working with a sequence of random variables in L2, they are assumed to be uncorrelated and we are also assuming that the variances are uniformly bounded. So, under this setting the same kind of argument goes through simply because the variance of Sn can again be written as just the summation of the variances of the individual random variables, and therefore we can repeat that same argument showing the required convergence holds first in L2 and therefore in probability. But now here we want to highlight the fact that uncorrelatedness is actually a weaker hypothesis, because first of all mutual independence will imply pairwise independence, which further implies uncorrelatedness. So, the mutual independence implying uncorrelatedness, this part is quite a weaker assumption than what we used in the proposition, but the same kind of proof will go through. Now, there is a important technique that is used in this type of results. These are called equivalent sequences of random variables. So, let us make the definition. So, we are going to say that two sequences of random variables, let us denote by xn and yn, defined on the same probability space, are equivalent if the probability that xn does not match with yn, those probabilities are summable. And if you observe this, then here is this very important consequence of this equivalent sequences. It is this, that if two sequences of random variables are equivalent, then as we have argued earlier in the 3 series theorem in the proof of sufficiency part. So, this was discussed earlier in theorem 2 of our first lecture in this week, that if we have sequences and look at their truncations, they had a certain relation between them that was used in the proof of sufficiency of the 3 series theorem. But now we can use the similar kind of a technique for two general sequences when they are equivalent. So, again using that similar kind of an argument used there, especially those the Borel-Cantelli related argument, you can prove the following statements, and this is left as an exercise for you. So, the first statement says that if two sequences xn and yn are given to be equivalent, then xn minus yn, if you want to look at the series corresponding to that, that will converge almost surely. So, that is the first statement. But then if you have that, then xn series will converge almost surely if and only if the yn series converges. You can get this very simply, because as long as the series corresponding to yn converges, then just add it to the almost sure convergence series as obtained in Roman 1. So, you get the convergence for summation xn, and conversely if you have the convergence for summation xn and by part 1 you have the convergence of xn minus yn that series, then from that you can extract the information about almost sure convergence of summation yn. So, therefore, Roman 2 will follow. Please write down the arguments. Now, we can also further scale this phenomena. So, suppose an is a sequence of real numbers such that an increases to infinity. So, without loss of generality you can assume them to be positive, but now look at these quantities, that you look at summation of the first n many xj minus yj and scale it by this an, and the statement says that will go to 0 in the almost sure convergence framework. And therefore, using the similar kind of a argument that was mentioned in Roman 2 part of this exercise, you can show that the sequence 1 by an summation xj's will converge almost surely if and only if the similar sequence converges for yj's. So, this is now another equivalent identification that we are stating. And finally, let us continue with this type of ANs, meaning these ANs are increasing to plus infinity. Then you can actually show that these kind of scaled versions of summation xj's, they converge to a random variable x in probability if and only if the similar combination for yj's will also converge to the same limit in probability. So, these kind of statements are following from the notion of equivalent sequences. So, please work out this exercise, and all of these are essentially using the Borel-Cantelli lemma type argument. And note that the idea is that whenever you are starting with a sequence of random variables xn, if this sequence is not easy to handle, what we can do? We can try to make certain changes to xn and obtain a equivalent sequence yn which might be easier to handle, and for yn you obtain the required results, and using this exercise you can essentially extract the results for xn. That is the usage of this exercise. So, please work this out, and using this kind of arguments, our weak law of large numbers type results that we have discussed earlier can be generalized further. We state it but without proof, and this result is typically called the Khinchin's weak law of large numbers. So, the setting now is this, that we do not assume that xn's are in L2 anymore, we just ask for finite mean. So, therefore, we want them to be in L1. Moreover, I want them to be pairwise independent only, but I would insist on identical distribution. So, now they have the same distribution, but if you are looking at two distinct xn and xm, then they are pairwise independent. So, under this setting, the conclusion holds that Sn over n, which is nothing but the sample mean, will now converge to the expected value. This is just a rescaling of our earlier result, because now you see expected value of Sn is nothing but summation of the expected values of all these xj's from 1 to n, but since all these random variables have the same distribution, this is nothing but n times expected value of x1. So, all these means are the same. So, that is essentially what is happening here, that if you want to put it in the earlier framework, you were looking at Sn minus expected Sn by n, but now this is exactly equal to Sn by n minus expected value of x1, and using our earlier statements, if we can apply them, these quantities go to 0. So, therefore, the restated version that we have is that Sn over n, which is the sample mean, converge in probability to expected value of x1. So, this is the weak law of large numbers due to Khinchin. So, all we are asking is that the sequence of random variables should be pairwise independent and they should be identically distributed. Moreover, they should have finite mean. Now, as a quick corollary of this weak law of large numbers, we can state the results for the IID case. So, of course, if the whole sequence is independent, then it will also be pairwise independent. So, therefore, we can apply our earlier result. But now, let us consider this IID case with finite mean. Then again, of course, the same result is true, that we have the in probability convergence of Sn over n to expected value of x1. So, therefore, we are having that the sample mean converges to expected value of x1 in probability as n goes to infinity. So, this is what we have discussed in terms of convergence in probability. Let us now move on to the case when almost sure convergence holds. So, that is the case for strong law of large numbers. So, let us see. So, we are interested now in certain situations when we can prove that the strong law of large numbers holds, and the next result is typically referred to as the Kolmogorov's strong law of large numbers. So, let us look at the hypothesis. So, what we are looking at is again this sequence of random variables in L2, and we will ask that should be mutually independent. Now, let us look at this sequence of real numbers which are positive real numbers with Bn increasing to infinity. Then we look at this specific type of a condition, that variance of Xn divided by Bn squared that series, if that is finite, then Sn minus expected Sn divided by Bn will converge in the almost sure sense to 0. So, this is a type of strong law of large numbers that we have been looking at. So, this is essentially getting scaled by Bn, and of course, special cases will be when Bn equals to n, and that is the case that will be a special case of this general case. So, let us see the proof. The proof is quite simple. We start by looking at variance of these quantities. So, look at the original random variables xn, subtract out their expectation but scale by Bn. Then what happens is that 1 by Bn squared comes out of the calculation, the remaining portion is just the variance of xn. But this is what we have assumed to be finite. So, that is our assumption, and therefore, by our earlier 2 series type theorem argument, what we are having is that these series of random variables must converge almost surely. Note that as long as xn's are given to be independent, this will imply that xn minus expected xn divided by Bn, these will also be independent. So, that is what we are using, and therefore, the corresponding series will converge almost surely by using this kind of variance type bounds. Now, observe that we can appeal to the Kronecker lemma that we have discussed earlier in the previous week of week 4. So, here what we look at is the term of interest, which is Sn minus expected Sn divided by Bn. That can be rewritten in this formulation, that it is 1 over Bn of this sum of random variables. So, here what we are doing, we are looking at xj minus expected xj divided by bj, but again multiplying by bj. So, this is just a rewritten formulation of the left hand side. So, this is very simple to verify, but once you write the left hand side in the right hand side formulation, we can appeal to Kronecker's lemma, and from the almost sure convergence of the series that we have established, from that we get the required almost sure convergence for Sn minus expected Sn by Bn. So, therefore, Kolmogorov strong law of large numbers will follow. Now, here let us look at this special case when all these xn's are IID. Then here all the variances are same, call it sigma squared. So, as long as this is positive, we are going to look at the scaling of this. So, here let us look at this situation, variance of xn over n. Then what happens is that first 1 by n square comes out, and we have to look at variance of xn, but variance of xn for all n is sigma squared. So, essentially we end up with this series, but this series converges, and hence the sufficient condition as part of the previous theorem holds. So, here we are looking at this specific type of a term where Bn is actually equal to n. So, therefore, if we appeal to our strong law of large numbers that we have discussed earlier, we have that Sn over n minus corresponding expectation will go to 0 in the almost sure framework, but then you just do the standard algebra and write that Sn over n now converges almost surely to expected value of x1, and therefore, also the sample means converge in the almost sure sense to expected value of x1. So, here it is noteworthy that in special cases of IID random variables, we have looked at the weak law of large numbers, which again gave us the similar type of a result, but it was convergence in probability. So, you can try to compare the assumptions and see where the difference lies. Now, using the idea of the equivalent sequences, which we have discussed in the case of both almost sure convergence as well as the improbability convergence, that was left as an exercise for you. The following version of theorem 4 can also be proved. We are not going to discuss the proof of this version. So, here what we are looking at is a sequence of IID random variables, but with finite mean now. So, we do not assume any more L2 integrability. So, that is dropped. So, we are only asking for L1 integrability that will ensure the finite mean condition. Now, as long as these are IID, all the corresponding mean, these quantities are some real numbers, and all of these are same because of the identical distribution. But then we look at Sn over n, and that converges again in the almost sure framework to expected value of x1. So, therefore, the sample mean converges almost surely to expected value of x1, provided we are working with IID random variables with finite mean. So, in this lecture we have discussed two types of law of large numbers. We have been looking at the essentially the limiting behavior of the sample mean. Here it is noteworthy that we have looked at these two versions, the weak law and the strong law, and we have looked at some special conditions under which the corresponding convergences hold. The convergences for the weak law are in probability, for the strong law it is in the almost sure framework. As long as you have the almost sure convergence, it of course implies the in probability convergence. So, in special cases we are going to look at either the strong law or the weak law depending on situations. And in the next lecture we are going to look at some applications of these laws of large numbers. We stop here. Thank you.